Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is motion problems involving acceleration due to gravity. We are currently in lesson 2 of the unit schedule, although because this is a big lesson and there's a lot of ideas to cover, we're only going to cover part of them in this video. So take a look here at the unit schedule and you'll see that in lesson 2 we're actually going to be doing section 2.4. I've highlighted this in red. These are the questions to and the reading to take a look at before class. Here are some problems that we'll do in class, and here are some extra questions you can try after class. All right, so there will be other videos on this lesson which will cover the other two sections, but for now, just the red stuff. Here are the learning goals and success criteria to look at, and also please have a look at the questions that we're going to address in today's video. You can pause the video right now and do that briefly. Okay, thanks, and you're back, and we're going to dive right into things here. So first off, I'd like to have you recall, how does gravity affect the motion of a falling object? And here is a picture of a lab being done at a school. Not quite sure what school this is. I found this picture online. It's not a picture from our school, but you can see right up here, these guys are using a spark timer attached with some clamps to some support rods, and a mass which is attached to the ticker tape is about to be dropped. And of course that's going to create these this dotted piece of tape that you're familiar with. We've already done a lab on this. We did it in the last unit, and you know that if you measure the acceleration of this, at least you're supposed to get 9.8 meters per second squared. Very careful measurements done of acceleration due to gravity indicate that to 2 significant digits, this is in fact the value at the Earth's surface. Now, another thing that we've seen from a previous video is the famous hammer and feather on the moon video, where one of the astronauts in one of the Apollo missions takes a hammer and a feather and drops them, and sure enough, in the airless environment of the moon's surface, they fall to the ground. Also in that video, or in a related video rather, you see that if you drop a hammer versus a feather in air, of course the hammer wins. You can try this at home if you have a hammer and a feather or a loose leaf sheet of paper. However, if you could drop these in an evacuated chamber, then they would actually fall at the same rate. So recall what this meant, which was that this 9.8 business is only true if there is no air resistance. If there is air resistance, then you're going to get a situation like this, where different objects fall at different rates. But as long as there's no air resistance to interfere, any object, either really heavy like a hammer or really light like a feather, will fall with an acceleration of 9.8 meters per second squared. And that, by the way, is the fact of the day, or the fact of the video. So I wanted you to recall this, because now we're going to look at how this value for acceleration here can be used to predict the motion of falling objects. Now, how are we going to do it? Well, since gravity is a constant force on any given object near the Earth's surface, therefore the acceleration that it produces is also constant. And if you recall what that means, whenever you've got constant acceleration, you can use the equations, the kinematic equations for constant acceleration. They are in your textbook. The textbook is Physics 11 by Addison Wesley. This is in section 1.6, so you have to go back a little bit. But here are 6 equations that can be used in this situation. So what we're going to be doing is applying these situations to instances where the acceleration rate, and I see acceleration there, I see it again here, see it here, I see it one more time here. We're going to be applying these equations to acceleration where the acceleration is equal to that of gravity, 9.8 meters per second squared down. So in all of these questions, you're going to hear words like an object is dropped, or an object is thrown in the air. And so we're going to know that gravity is the only force acting. Well, strictly speaking, there will be some air resistance in real life. However, we're going to assume no air resistance for most of our problems, because that way we can use 9.8 no matter how heavy the object is. Now, as you go through this part of the unit, you're going to see terms, of course, like V1. And while we knew that V1 meant initial velocity in the past, and it still means initial velocity, when we're talking about an object thrown in the air, we sometimes also call it the launch velocity. So you may hear the words, a ball is thrown up. They're talking about the initial velocity here, if they give you a speed or a velocity. Okay? A v2 would be a final velocity, and this could mean any number of things. It could mean the very final velocity, like when the object hits the ground, perhaps. Or it could mean any other final time. For example, you're going to see a question today where we're going to calculate what's called the maximum height of a ball thrown in the air. And since we know the starting velocity, therefore the final velocity will have to be at that point where the ball reaches its maximum height. So v2 is not always when the ball impacts the ground. It's just not the initial velocity. It's the velocity at any other time where we're curious to know something about the motion. You have to read the question carefully to decide. You'll also see us using time. This will refer to the total time spent in the air during the question. Sometimes this is referred to as hang time, which is kind of a football term. If you watch American football, they sometimes refer to the hang time when the football is up in the air. So you may hear this mentioned as well. And finally, you'll see displacement. Remember what displacement used to mean. It used to mean the straight line from start to finish. You calculated a vector. Well, it still means the same thing. You throw a ball in the air and it either lands, or we talk about what it's doing at some later time. Draw a straight line from the start to that final point. Its distance and direction are the displacement. So really we're just slightly adapting these equations to vertical up and down motion due to gravity. Here's what I'd like you to do right now. Try this. Take any object, it could be a ball, an eraser, a pencil, anything that's near you and not fragile preferably, and throw it up in the air, allowing it to land on the floor. Can you identify each of the variables in this chart? Can you identify when and where each one applies? So as you throw that object in the air, which of these is the V1? What would that look like? As it hits the ground, which is the V2? Which is delta t? And which one is the displacement? Pause the video for a moment, throw something in the air, let it land, and see if you can identify each of these four variables. All right, and you're back, and now we're actually going to try to solve some problems involving these. So let's have a look at one. This is kind of a classic one. I'll read it to you. It's about something called maximum height. A ball is thrown upward from a height of 2 meters above the ground. So picture a person throwing the ball in the air. Its initial speed is 15 meters per second. And because we know it was thrown up, therefore we also know its velocity, we know its direction. What is the ball's maximum height above the ground? Now the first thing you should do is draw a picture to get an idea of what's really going on here. So here's the ground, and here's a physics student who is throwing the ball upward. Now it says that the person throws the ball from a height of 2 meters. So I'm going to show 2 meters is the starting height. This could be important, so we should write it in. It says that the ball was launched upward at 15 meters per second. So I'm going to show with an upward arrow 15 meters per second. And then I'm going to ask myself, what symbol are these two things? Well, if you go back to this chart here, you can probably identify that v1 is the starting velocity. So let's put that in. This is v1 equals. But what is the 2 meters? If you think about this, the ball is going to go up, 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 and then it's going to come down, 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 down like that. But the question doesn't care about the part where it's coming down here. All the question cares about is what is the maximum height. And if you look at what's going on here, the maximum height is right over here. So we don't really care about too much information after that point. What we do care about is how high up did this go? And if you drew a good picture, you'll be able to see that in order to answer the question of how high above the ground did the ball go, we also need to account for the 2 meters. So I'll put a little star there so that we don't forget. But can you see how you would solve this? If only you could figure out the extra distance going up. You could add it to the 2 meters and you'd get your answer. So what variable is that extra bit that the ball goes up? Well, that would be a displacement, a straight line from start to finish. In this question, the start is obviously the launching, and the finishing is up here. So we can actually start writing some information up here. For example, do this right now. In a second, I want you to pause the video, take an object, a pen, pencil, eraser, throw it up a little bit in the air, and watch it at its maximum height. What does the ball do? Or what does the object do? Do this now. Okay, and you're back, and I hope you realize that the thing the object does, aside from reaching its maximum height, is it stops moving. It stops going up, and it gets ready to come down. So the v2 is actually 0. Now there's one more piece of information that we need in here, and that is to realize that the ball is moving under the influence of gravity. So even though they don't tell you that, you're supposed to be sharp enough to pick up that the acceleration is actually 9.8 meters per second squared. But now I run into a little bit of a problem here. Here's the problem. v1 was up, indicated by this arrow, but I know the acceleration is down. We have to include vectors, vector directions, when we're talking about vectors, obviously. So how are we going to deal with this? Well, there's two things you can do. You can write square brackets with arrows so that, for example, v1 is up, acceleration is down. Of course, because we know that up and down are just negatives of one another in terms of direction, here's another little trick you could do. You can call positive the upward direction. If you say positive is the upward direction, then that means negative is the downward direction. And now watch what we can do. v1 can be thought of as a positive velocity. v2 being 0 obviously doesn't have a plus or minus. But acceleration of 9.8 down can also be written as negative 9.8 meters per second squared. And recall that the thing we want to find out here is how high up does this ball go beyond the launch point. We discussed how that was a displacement, so I'm going to write that in. We're going to add that to the 2 meters and get an answer. Now I've written the answer down here, but I'd like to take you through how you might actually solve this. Remember what you did with kinematic equations? You wrote down what was given, you wrote down what was required, and you looked for an equation to link those up. So let's do that again, because really this is just kinematics. We have v1, we figured out v2 because it's a maximum height question, we know the acceleration, and I believe that's all we know. We want delta d, and now we need an equation. So where's the equation with v1, v2, acceleration, and delta d? Let's have a look. Pause the video now and look through these equations and see if you can find one. All right, and you're back. And I think you'll find that actually there isn't one that gives you everything all in one shot. There are some equations with v2, v1, and a, but that has delta t, not delta d. Then there's one over here that has delta d in it, but you need to know time as well. So can you think of a strategy here? How about this? Why don't we use the fourth equation here to get the time? And then once we have the time, we can sub it in to the fifth equation here, and then we can get the displacement. So here's what I'd like you to do, and I'm going to have you finish this off on your own, but there are two equations that you have to use here. Let's write out what they are. In the first step, you're going to use v2 equals v1 plus a delta t. And of course, you know v2 is 0, v1 is positive 15 because it's up, plus the negative 9.8 of acceleration times the time. So this is going to get you time. I'll leave it to you to solve that. And then the second step will be to take that time and use it in this equation over here, which has delta d in it. So at this point, you can say delta d equals v1, which you know, plus v2, which you know, divided by 2, these are vectors of course, make sure you include direction, times time. So that gets subbed in there, and voila, you can solve for delta d. Don't forget to add on the 2 meters, and you should find yourself getting to your answer here. So that's how to do a maximum height question. It's to realize that v2 is 0 at maximum height. And of course, don't forget to add any extra distance here if the ball was not launched from ground level. Let's move on now to another classic question. This is a question about something called hang time, which we've already discussed what it means. It means how long is the ball in the air. So this is actually the same question. I've kind of rewritten it, maybe with a little bit different wording. A ball is thrown upward from 2 meters above the ground, initial speed 15 meters per second. How long will it remain in the air? This is not asking me what the maximum height is. It's actually saying how long will the ball stay in the air until it hits the ground. Didn't say anything about maximum height. So you have to realize, you have to read into this a little bit. Got to use your best judgment here. They don't always tell you, but you guys are smart enough to maybe figure things out a little bit on your own, or if you're really stuck, you can always ask someone for help. So here we go. The ball started from 2 meters up, like this. It was launched upward with a v1 of 15 meters per second. I think we said positive would be the upward direction. We realized that A will therefore be negative 9.8 because gravity points down. Only this time the ball is going up, 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 up. We're interested in also the down, 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 down part. We want the total time, and we have to take into account that the ball started from 2 meters above the ground as well. Anything else that we know? Do we know the velocity at impact? Let me use a different color there. Do we know the velocity at impact? I'd like you to pause the video for a moment and just answer that question. Do you know the impact velocity? And if so, what is it? Okay, and you're back. If you think about it, you might imagine throwing a ball in the air, having it land and hit the ground and stop moving. Sometimes an object that hits the ground stops, but other times an object bounces. Sometimes it starts rolling somewhere. It's really hard to tell what exactly is the velocity when an object hits the ground. So this might not be the best idea to use this concept for our kinematic equations. I'll give you a hint. You know that the ball started over here, and it finishes down here. What do you know for sure, for sure, for sure? You know that it ended up 2 meters below where it started. How do we write that in physics? Easy. Delta D, displacement, is negative 2 meters. This one is guaranteed correct. No one can argue with this. But what is the impact velocity? Does the ball stop when it hits the ground? Does it bounce? Does it roll? No one knows for sure until we try it. So don't use this idea. Definitely use this idea. So let's make our given and required and link chart. Let's link these up with an equation. What are we given in this question? Well, we're given V1. We are given delta D. We are given the acceleration. And we're asked for the time, right? The hang time. What is the equation to use? Well, let me create a little bit more space here by shrinking that down, because I'm going to need a little bit of room. There we go. What equation should we use? Well, let's go back and have a look at what's available. Pause the video for a moment and have a look. Okay, you're back. And if you picked equation number 6, you're right. This one will give us what we need. So let's go back over here and let's start writing. The equation we need is delta D equals V1 delta T plus a half A delta T squared. Vectors all around. Let's plug in the numbers. Negative 2 equals V1 15 times the time plus a half of negative 9.8 times the time squared. Now, what do you notice here? Here's a variable raised to the first power. Here's a variable raised to the second power. It's quadratic time, folks. So what do you do here? Remember how to solve a quadratic? Get all of your terms onto one side and get 0 on the other side. So here's how we're going to do it. The negative 2 will stay on this side. This, which is a half of 9.8 delta t squared. A half of 9.8 is 4.9, and it's negative. So when I bring this across, that'll become positive. So I'll have 4.9 times the times squared. This term over here is 15 delta t. When I bring it across, it'll become negative 15 delta t. I'm keeping the negative 2 on this side. All that's left is 0 on that side. Here's your quadratic. What are you going to do now? This is the number in front of the squared term. This is the number in front of the non-squared term. And this is the number that's all by itself. Remember this? Delta t equals negative b plus or minus the root of b squared minus 4ac all over 2 times a. Here's your a. There's your b. Don't forget the negative. There's your c. Plug this in, and you're going to get 2 answers. You're going to find that one of them is negative and one of them is positive. The positive one is this. The negative one, I think, is something like negative 0.1 or 0.2. Since there are no negative times allowed, you're going to pick the positive one, be happy, and away you go. Does 3 seconds, 3.2 seconds make sense for an object thrown upward at a decent speed to then come down and drop an extra 2 meters? I don't think it's way out of reason. If you got something like 40 seconds here, I would really start to wonder if I made a mistake. 40 seconds for a ball thrown in the air by a person from 2 meters up doesn't sound too realistic. If the ball stayed in the air for just 0.1 seconds, I would be equally suspicious. But in my experience, throwing a ball up pretty hard from, a person's height is about right, a few seconds in the air. Sounds good. Let's try our final question here. This is a question about impact velocity, which we did discuss in the previous question. Remember when we decided it's hard to know impact velocity without doing a calculation, so don't assume you know what it is. Now we can talk further about that. It's the same question here, where a ball is thrown up from 2 meters above the ground at 15 meters per second. Positive is up. This is 2 meters here. You can see I'm going quickly here because we've already covered this stuff. The ball goes up, 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 down, 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 and they ask for the impact velocity. That means the velocity when the ball impacts the ground, right here. Does the ball stop? Is the impact velocity 0? Does the ball bounce? Does the ball roll somewhere? We don't know. Better calculate. Better not assume anything. We also know for sure that acceleration is negative 9.8 meters per second squared. All right, so here we go. How are we going to solve this one? Again, you're going to make a given, a required, and an equation chart. The given numbers or values are V1, A, and delta D. Remember, delta D is the negative 2 meters that we talked about due to the ball starting here but ending 2 meters lower down. The required information is a V2. So what equation are you going to use? If you take a look back at the list of equations, once again you'll see there is no equation that has all of these. However, you could use equation 4 to get the time. Sorry, I'm lying there. I don't think you can do that. Let's take a look at what we have here. We have V1A delta D. We want V2. You're going to need another approach. We have V1, A, and delta T. So we can use this one to get the distance. Sorry, I'm making another mistake here. Hold on a sec as I pause the video and see what am I thinking. Hold on one sec, folks. Okay, I'm back. Sorry about that delay. Every now and then my brain freezes. It can happen to the best of us. You are going to use equation number 6. You know the delta D. You know V1. You know the acceleration, but you don't know the time. Although, think about it for a minute. Do you know the time? I'll give you a hint. You solved for it here when you did the hang time. But imagine you hadn't done this question already. You wouldn't know the hang time. You'd have to do this quadratic again. But I guess you could cheat here, or, well, it wouldn't really be cheating. It would be more like using your resources, probably a smart thing to do. So use your time from here if you wish. And then once you have the time, and you're looking for V2, you can use equation number 4, which has V2 equaling V1, which you know, A, which you also know, and the time that you would have just found. So let's go back over here and say that the first step is we're going to use delta D equals V1 delta T plus a half A delta T squared. And I'll put a little mark here, found in previous question. You're going to solve for time. And remember, that'll be a quadratic. So there are 2 times. Make sure you choose not the negative one. The second step then will be to use V2 equals V1 plus A delta T. You're going to sub the time into here, and that'll get you V2, the impact velocity. And check that you do in fact get 16.3. Should be down. This is one way to check that you're doing things correctly. If the answer doesn't come out negative, you'll know you made a mistake, because this ball is definitely on its way down at impact. All right, folks, so there are 3 examples of how to solve kinematic equations involving acceleration due to gravity. There is a word problem component to this, so it can get tricky. Make sure you know what all of those terms like impact velocity and hang time and maximum height mean. Get used to using all of these in the context of the kinematic equations. Remember that for all of these, the acceleration is 9.8 meters per second squared down. And I think if you can keep all of that straight, then you are going to be successful with solving these. Thanks for watching, and I'll see you in class. Bye now.